Hello everyone, just a heads up, I'm filming by an open window today, so if you hear any bird noises or any cars going by, my apologies for that. It's just a little bit too warm here in my house for me to be closing up all my windows, so we will just have to make do with what we've got. So our objective for today is that students will be able to solve for missing angles by using the inscribed angle theorem. And that's the big thing we're going to talk about today. You'll see what that is in just a couple of minutes. So our application for today we're talking all about circles, inscribed angles, central angles, all of these new things. And when we're talking about circles, a lot of the concepts that we'll be talking about are really useful for engineers when they're designing anything circular. So the specific example that I chose to talk about here is amusement park rides, because I think they're a lot of fun. And they're a lot of fun for us to think about what engineering goes into that. So anything circular in an amusement park, like Ferris wheels, carousels, that sort of thing, all of those have design elements that depend on things like the inscribed angle theorem. Extra fun fact for the day, the word Ferris in Ferris wheel is always capitalized because Ferris is a name. I didn't know that until today when I was researching some application things having to do with circles, and I found out that Ferris is actually the name of one of the first engineers to work on a Ferris wheel. So, fun fact, if you'd like to learn more about Ferris Jr. and his Ferris wheel, which I believe was in Chicago, you can go ahead and do some Googling on your own. All right, so go ahead right now. Let's pause this video, do what you do every day. Let's put in right here one application you can think of where thinking about angles and circles together would be really useful. Thank you for working on that. Now let's move on to some notes, and we're going to start with some vocabulary. So an arc is actually a really easy vocabulary word. An arc is just part of a circle. So if I have a circle here, if I just take a section of this circle, like this section here, that's an arc. If I take a different section of the circle, this section here, that's also an arc. Now let's talk about the difference between a major arc and a minor arc. So if we're given 2 points, the major arc is the larger distance. So this is the larger arc, and the minor arc is the smaller distance. So let's say, for example, I have a circle, and I'm going to make this circle big enough to where it's going to be the picture for both the major and the minor arc in this example. So let's say that I have an angle here, right? So if these are the 2 points that I care about, right, given 2 points on my circle, like let's say this is point A and this is point B. So given 2 points on my circle, the major arc is the larger distance. So that's the bigger arc, right? So my major arc is this red one that I drew here. And my minor arc, it's still between point A and point B, right? But it's the smaller arc. Now let's move on to an inscribed angle. So an inscribed angle is an angle made from 3 points on a circle. So with this angle that I made up in our major and minor arc example, right, this angle here, this center point, I made that the center of my circle rather than being on the circle itself on the outside. An inscribed angle is an angle in a circle where all 3 points of the angle are on the outside of the circle, right? It's on the circle's edge. So this would be an example of an inscribed angle because it's made from 3 points that are on the circle itself. Now, a central angle, we've already seen an example of. A central angle is an angle whose vertex is the center of the circle. So what that means is if I make a circle, if my center of my circle is the vertex, any angle coming out from that center is going to be a central angle. And that makes sense because we know a central angle starts in the center of the circle. Now, an intercepted arc of an angle, this is the last vocabulary word we are going to go over today. So an intercepted arc of an angle is the arc formed by the two non-vertex points of an inscribed angle. So generally when we're talking about this arc, we're talking about the section of the circle that does not include the vertex of the angle. I'll show you what I mean in just a moment. So if I have an inscribed angle, right? So I have 3 points that are on my circle that are making my angle. The inscribed arc is this portion of my circle. Right? That's the inscribed arc. And the reason that we choose this portion of the circle and not this portion of the circle is because this point would be included if we chose the larger portion. So we always choose the portion of the circle that does not include this point. So in this case, that's the red portion. All right, let's take some of these vocabulary words and start thinking about them a little bit deeper. Okay, so here we have an exploratory challenge, and this challenge says, in the circle below, draw the angle formed by connecting points B and C to the center of the circle. So we can make those two line segments that connect B and C to point A. And our first question says, is angle BAC an inscribed angle? Explain. So go ahead, pause this video, and in this box, I'd like you to write just a sentence or two about whether or not this is an inscribed angle and tell us why. Thanks for pausing and working on that. Hopefully, you looked back at your vocabulary words. And looking at this angle, right? We can see, is this an inscribed angle, an angle made from 3 points on the circle? Well, if I look at my 3 points, B and C are both on the circle, but point A is in the center of the circle. It's not on the outside. So this is not an inscribed angle. Now, if you didn't get this right, you don't have to go back and change it. Just remember that this is not an inscribed angle. This would actually be, if we look at our definition, we would say that this is a central angle, right? Because the vertex of our angle is in the center of our circle, right? A is in the center of the circle. Now, if we look at part C asks us, is it appropriate to call it the central angle? Why or why not? Go ahead and share your thoughts there. This is a great discussion question, and I'm really curious to see what you guys have to say, so I'm not going to go over the answer here. Let's move on. So part D says, what is the intercepted arc? Now we can remember that an intercepted arc is the arc that's formed in between the 2 points on the outside of the circle, right? So if we're looking at this angle, we really have 2 intercepted arcs, right? We have this small arc, which we know is the minor arc. And then we have this larger arc, which is the major arc. Now, the way we write arcs is using this notation, BC with a little arc over top of it. If you're typing, don't worry at all about putting that arc symbol over top. There's no reason for you to stress out about it. That symbol, if you're writing it on paper, it looks like a sideways parenthesis that you're putting on top of your letters. Now, typically, when we're talking about an intercepted arc in a situation like this, we're talking about the minor arc. If you instead wanted to talk about the major arc, if you wanted to define that you were talking about the major arc rather than the minor one, the way that you could do that is by putting an extra point on your circle, like anywhere within your major arc, like point D. And you could instead say, I'm not talking about arc BC, which is the minor arc. I'm talking about arc CDB, which starts at C and goes all the way around to D and then goes all the way around to B. So that would be a way for you to symbolize the major arc. Another thing you could do is you could just write that you're talking about the major arc. So you could say arc BC, I'm talking about the major one. Or you could write out major arc BC. So you have lots of options there, but typically we will be looking at the minor arc instead of the major arc, so you shouldn't encounter this very often. All right, let's move a little bit forward. Now, part E says, can you make a prediction about the relationship between the inscribed angle and the central angle? Now, what this is asking is, how do you think if we had the inscribed angle, we could calculate the central angle or vice versa? Now, you don't have a lot of experience with this yet, so I'm going to talk us through just one or two examples, and then we're going to make a prediction, and then we'll see what the answer is. So before you work on that reflection question at all, let's look at what would inscribed arcs look like, right? So if I'm looking at this arc, this minor arc that's formed by angle BAC, which is the central angle, what if instead of a central angle, I had an inscribed angle? So instead of angle BAC, what if I had angle BDC? I want you to think about, is this angle smaller or larger than the green angle BAC? Now, what if I put my point somewhere else? What if we put point E here? Well, what size would angle BEC be? Would it be smaller or larger than angle BAC? So when we're thinking about the size of the major and minor arcs, make sure that you're thinking about the actual size of the angle, right? This size, what we would measure if we had a protractor, rather than the length of the legs of the angle, right? I don't care how far it is from D to C compared to A to C. I care about how big this angular distance is in each of these angles compared to the angular distance in my green angle here. So what I would like you to do down here in part E, I'd like you to pause this video and compare the inscribed angles, so the black angles that included points E and D, and the central angle, which is that green angle. Which one do you think is bigger, and why do you think that? In this box here. All right, thanks for working on that. Let's move on to our examples. Oh, sorry, this is a little bit of a formatting error. So the examples are on the next page, but this example says, using a protractor, measure both the inscribed angle and the central angle shown on the circle below. So let's look at that circle. Now the angle that it's talking about, the inscribed angle, we're going to make that our black angle. So that's this angle right here, angle DCB or BCD, either way. So we're talking about this angle, and it's asking us how big is that angle. Now, you guys don't have protractors at home probably, and this is probably on your computer or your phone. So it might be really hard for you to measure this. But what you can do, as long as your aspect ratio is the same as mine is, you could take a piece of paper or a book or anything, and you could hold it up to this black angle here, and you could see that this is actually a right angle. Now that means that we are going to use this symbol for the angle instead of the rounded one, because this is the symbol for right angles. And we know that right angles are all 90 degrees. Like I said, if we were in the classroom, we would be measuring this using protractors, but we don't really have that option at the moment, so we're just going to make do. Now, the second angle that they're asking us about is the central angle, angle BAD. Remember, we call this a central angle because it includes the center of the circle, which in this case is point A. So angle BAD is actually a straight angle, right? And we know that straight angles, lines, are actually 180 degrees. So in this example, the inscribed angle is what compared to the central angle? Well, we would say that 90 and 180, if you saw those two numbers, hopefully you realize that 90 is half of 180. Now this should start to get your mind working and saying, oh, the inscribed angle was half of the central angle in this example. I wonder if that will be true in the future as well. And the interesting thing is, our next theorem, or the first theorem we're going to talk about, the next thing on our page, is actually the inscribed angle theorem. And you'll recognize the inscribed angle theorem from our objective at the beginning of the lesson, where our goal for today is to use the inscribed angle theorem to solve for missing angles. So here we're really hitting on that goal. The inscribed angle theorem says the measure of a central angle is twice the measure of an inscribed angle that intercepts the same arc as the central angle. Now this is getting to a really important part of how we talk about arcs. Right here, we have an 80 in this example, right? Now I'm going to hit on this picture for a moment, and then we're going to go back to the theorem to think about that for a second. This 80 degrees is the measure of the arc. So we would say the measure of arc BC, and we know that we're talking about this 80 degrees because that's the minor arc, and we always assume that we're talking about the minor arc in these situations, is 80 degrees. What does that mean? Well, if we're saying that the measure of an arc is 80 degrees, we're saying that if we made a central angle with those 2 points, if I connected those 2 points to the center, then this angle would be 80 degrees. So that means that the measure of the arc is always equal to the measure of the central angle. That's not on this notes sheet anywhere, but you might want to write it down, right? So the measure of the arc is always equal to the measure of the central angle. Okay, well that's great. The measure of the arc is equal to the measure of the central angle. Awesome. But what does that mean for this inscribed angle down here, angle A? Well, this is where we're really going to dive into our inscribed angle theorem. The theorem says, I'm going to read it one more time, the measure of a central angle is twice the measure of any inscribed angle that intercepts the same arc, right? Now this arc BC, is being intercepted by this central angle with the center of the circle, and also by this angle that includes point A. That means that the central angle is twice as big as the inscribed angle. So if our central angle is 80, and that's twice as big as our inscribed angle will be 40 degrees. Now we could write this as an equation if you wanted to, right? So you could say the central angle is the inscribed angle times 2. Or you could say the inscribed angle is the central angle divided by 2, or times 1/2, right? So you could use these equations if they help you, but really what we want to be doing is just thinking about the fact that the central angle is twice as big as the inscribed angle, or the inscribed angle is half the size of the central angle. Either one of those will work for you. All right, let's move on to our second circle here, our second example, and see what we can figure out. So this example asks us about some arcs. It says, can you find the measure of arc AB? And remember that the measure of an arc is the same as the measure of the central angle. And we're always thinking about the minor arc when we just see two letters, right? So we see two letters, we're thinking about this minor arc. We know that this arc is intercepted by this central angle, angle OAB, and we know that the size of that angle is 110 degrees. So that means that the size of this arc is 110 degrees. So the measure of arc AB is 110 degrees. Now let's talk about the major arc ACB, right? This major arc here. Now that major arc is the rest of our circle, right? Now if we had an angle that spanned an entire circle, right? So if I had an angle whose beginning and end was at the same place and I was going the whole way around the circle, we would say that that was 360 degrees, right? So if I want to find the major arc, all I have to do is subtract from 360 degrees. I just take 360 degrees, which is my entire circle. Then I subtract off the arc that I have, that minor arc. I subtract the 110, and then we get 250 degrees. So that means that arc ACB, our major arc in this case, is 250 degrees. Now I'm going to add one more question here for practice for us. And that is, what would the measure of angle ACB be? Okay. Now let's draw angle ACB. Angle ACB, if this is point C, would look like this. Now here, again, we have an inscribed angle that we're comparing to a central angle, right? And that inscribed angle is ACB. The central angle is AOB. So we have to use the inscribed angle theorem, which says that the inscribed angle is half of the central angle. So all we have to do is take that 110, divide it by 2, and we should get 55. You can put that into your calculator if you need to. So 110 divided by 2 is equal to 55 degrees. So that means that the measure of angle ACB is 55 degrees. There's one more theorem we're going to talk about. This is a really important theorem that follows from the inscribed angle theorem, and we could prove it, though we're not going to do that today. This theorem says inscribed angles that intercept the same arc are equal in measure, right? So let's say that I'm looking at this arc, arc AB. Now there are two angles that intercept that arc, right? Angle ADB intercepts arc AB, and also angle ACB intercepts arc AB. Now the important thing about that is if we knew the measure of arc AB, like let's say we knew the measure of this was x, which we know is equal to the measure of the central angle, right? We know that we would divide x by 2 to get either of the intercepted angles. So that means that the angles are equal in measure. So let's just write that down so that we can use it later, right? This means that the measure of angle ACB is the same as the measure of angle ADB. Now there's another arc that's intercepted by two different angles. For example, we could use arc CD. This is intercepted by both angle CAD and also by angle CBD. So that means that the measure of angle CAD is the same as the measure of angle CBD. Now that might not sound very important, but when you get to some further questions, And really, if we were deep diving into more difficult questions in the classroom, you would use this idea a lot. All right, so now you have enough information to work completely on practice level 1. So if you feel like you're just going to do the level 1 practice and you want to go work on that right now, you can certainly do so. But if you want to do the level 2 practice, which is some more of those more difficult questions, you really want to dig deep into this concept, stick around for some additional facts that are going to help you out. So the first idea we have here is the relationship between right triangles and diameters of a circle. We got a little bit of a hint of this in a previous example problem, but let's take a look at it more in depth now. Let's say I have a circle and I have a diameter of that circle. Now remember that a diameter is a straight line segment that starts and ends on sides of our circle, right? But goes through the center of the circle. Now, if I have a diameter, what's the measure of that angle? What's the measure of this central angle? Well, we talked about that a little bit before. We know that this measure is going to be 180 degrees. Now, what that means is that this measure up here is also 180 degrees because they're both straight lines. They're both straight angles, right? So if I'm looking either at this as an intercepted arc or at the bottom half as an intercepted arc, I'm going to look at the top half right now, right? If I'm looking at this blue section as an intercepted arc, I know that that arc has the same measure as the central angle, which I know is 180 degrees. So that means that I know that any inscribed angle intercepting that arc will be half of 180 degrees, which is 90 degrees, right? So that means that any point that I put on the other half of my circle is going to make a right angle. And that means that if I use that point and the 2 points made by my diameter, I'm going to get a right triangle. And that works for any triangle that I make from 2 points on a diameter and a third point. So if I put a point over here, that means that this blue triangle is a right triangle. If I put a point here, it means that this green triangle is a right triangle. So the next part that we want to talk about very briefly and quickly is the fact that you can add and subtract arcs that are next to each other or that are part of circles. Now we saw this a little bit when we were talking in the second example under the inscribed angle theorem, right? We talked about the fact that if I have a central angle here that tells me what this arc length is, that I can subtract that from 360 to get the rest of my circle. But that works in other situations too, right? So if I had, for example, cut this in half, and then I had this inscribed angle here. So if I were given the measure of this arc and the measure of this central angle, for example, then I could figure out this inscribed angle by first subtracting and then figuring it out. Let's put some numbers on this and just do a really quick example. So if I know that this minor arc is, let's say, 80 degrees, and if I know that this central angle is 45 degrees, then if I want to get this arc, right, this section, I would just do 80 minus 45. And I should get 35 degrees. So that means that this small section is 35 degrees. So I know that this central angle is 35 degrees. And to get the inscribed angle, what I would do is divide that by 2. And that's not going to come out quite evenly. It should come out to, I believe, 17.5 degrees. So 35 degrees divided by 2 is 17.5 degrees. This is pretty intuitive, the idea that you could add or subtract arcs. We do the same thing with angles, and we've done this a lot with angles so far. So I think that if you're trying to use this idea, you'll be able to be pretty successful. Now let's move down to inscribed quadrilaterals. and we're just going to talk about one concept here as well. The idea with inscribed quadrilaterals, remember that a quadrilateral is something with 4 sides. That means it also has 4 vertices, right? So if I pick 4 points on my circle and I connect them, this would be an inscribed quadrilateral. It's inscribed because each of your angles are inscribed angles. Now, what a lot of questions having to do with inscribed quadrilaterals will do is it will give you one angle and it will ask you to find the opposite angle. So let's say in this situation, it gives you this angle and it says that it's 50 degrees. And it wants you to find this opposite angle. Now, what that's asking you to recognize is that this 50-degree angle intercepts this arc, and our question mark angle intercepts the opposite arc. So if I were to try to get, let's give my circle a center here. If I were to try to get, okay, what's the size of the green arc? Well, I make my central angle, right? I know that this 50 degrees is half of what I need, so I need to double that. So that means that this green arc is 100 degrees. And then I need to think, okay, if the green arc is 100 degrees, what's the red arc? I know that I'm going to get that by subtracting from 360. So I'm going to get 260 degrees. And then if I want to get my mystery angle intercepts this red arc, right? So since that mystery angle intercepts that arc, I'm just going to divide that by 2. And I get 130 degrees for my mystery angle. Now, I'm going to put a challenge out there to anyone who has watched the video this far. I will give you bonus points, especially for my students, and I'm sure that Mr. Rodriguez and Ms. Yagi would do this as well. I will give you bonus points if you can show me an easier way to do this. If you can show me the relationship between the opposite angles that does not involve you finding each of the intercepted arcs and multiplying by 2 and dividing by 2 and doing all of those steps, if you can show me how to do it in one step, I will give you a whole boatload of bonus points and like lots and lots of Ms. West bonus points in my heart as well. Because I would be really impressed if any of you guys could figure that out. All right, so I know this is a new concept. I know it was something really new, but thank you so much for watching the entire way through and really working on this. We look forward to working on circles because they're a really fun topic, even though we don't have a lot of time to sit with them. So I hope everything is going well for you. Please let us know if you have any questions and come to online help if you need it. Have a wonderful day, everyone.